Public Key Infrastructure, or PKI, is a collection of technologies used to apply cryptography principles. It is based on a practical distribution and implementation of keys with a set of tools to achieve confidentiality, integrity, non-repudiation, and authenticity. The implementation of PKI is a strategic process aimed at reducing risk related to security at a global level. PKI is very extensible, and it can be used for a variety of purposes. The core principle of PKI is trust, and it often relies on a third party to achieve that trust. PKI creates a relationship between the various components in a session, which allows the components to prove their identity and the origin of the secured information. In this module, you will learn about the core components of PKI, namely digital certificates and certificate authorities. You will learn how certificates are created, how they are used, and what benefits can be derived from them.
So I have a question for you. Have you ever thought about, do you trust your bus driver? Do you trust the people that make the food you eat at a restaurant? Do you trust the sales clerk at the checkout counter? Now, these are all questions that you don't often ask yourself on a regular basis, but in fact, that you actually rely upon them to perform tasks for you, that you depend upon them to provide you, say, food or service that's going to be safe and reliable, is a expression of trust. Now, in this module, we're looking at PKI, Public Key Infrastructure, which is a way of implementing trust structures through the use of cryptography, and specifically the use of public key-based digital certificates. Public Key Infrastructure, or PKI, is the idea of implementing cryptography and related technologies in such a way to have a real-world business-usable security system, where you can have secure communications and secure storage. Now, sometimes PKI is described as being a security infrastructure or being a security template or even a security framework. I'm not sure these terms are all that clear, so think of it as a security recipe. It defines you should mix together 4 main components in order to get something usable out of it. Those 4 components are symmetric encryption, asymmetric encryption, hashing, and the use of digital signatures for your authentication. So with these 4 components mixed together properly, we have a PKI solution. So PKI is a way of bringing in reliable, trustworthy security to computer communications, again, both for storage and for transmission. It allows for the benefits of all 4 possible security services available from cryptography. Again, those are confidentiality, integrity, availability, and non-repudiation. It also is based upon the idea of having trust relationships and developing those relationships over time. And trust is often defined both by the technology in use, but also by the entities that are already trusting someone. This is sometimes known as trusted third-party environments or trusted third parties. We'll be taking a look at this and other details of PKI in this unit. Let's explore some of the more detailed components that make up PKI. So we've discussed the basic idea that there are 4 main parts of PKI in general: symmetric encryption, asymmetric encryption, hashing, and then digital certificates used for authentication. It's this last section we haven't spent much time on yet, so let's do that now. So certificates are a special application of asymmetric public keys and private keys to provide for authentication. This is done via a system called a certificate authority, or CA. A certificate authority is an entity who will accept requests for new certificates, will check and verify that someone is who they claim to be, and then will issue a certificate to them. Now let's say an entity here, which may be any business, would like to get a new certificate. Maybe they are running a web server, for example. They would go to a certificate authority to make their formal request to get a certificate issued to them. Now, certain certificate authorities have decided to offload this particular task to a dedicated entity called the registration authority. And this may be a separate part of the CA's business itself, or maybe an outside company that does this work for them. The registration authority will accept the inbound request, will then process and verify to some minor extent, or maybe major extent, that the entity that's making the request is who they claim to be, and then file that with the certificate authority. Now, in many cases, the CA may be using certificate templates. A certificate template is a pre-configured list of certificate settings. This can help automate the process of issuing certs for users and computers without it having to go through the complex formal registration process. This is usually done for private CAs for employees and valid internal devices, not necessarily often used on the public internet. Now, once an entity has a certificate issued to them, users would then try to visit and use their services. So over on the right here, we have an entity, we'll call him the user. And when this user interacts with their server, they will be verified that the business is who they claim to be because their certificate will be sent to the user. Now, the user's system will then check and verify that the certificate is valid. This is done in a multi-step process, including checking that the user already knows and trusts in the certificate authority that issued the certificate, that the certificate is still time valid and has not yet expired, and third, that the certificate is still valid and has not been revoked. The idea known as revocation is when a certificate authority cancels a certificate. When this has been canceled, you want to be aware of this and not accept canceled certificates. And therefore, you will check with a revocation service of some sort to figure out, is this still valid or has it been canceled? If all these elements check out, then the certificate is valid and you can now accept the identity of the claimed subject, in this case, the business or website you're visiting. What is important to keep in mind, however, is that digital certificates only tell you who someone is. They do not verify that someone is trustworthy or that you should put your trust in them. So think of it this way. Certificates tell you who to blame, not who to trust. So a certificate authority is the entity that issues certificates. It does so as a means to help verify who someone is in a trusted third-party situation, where the certificate authority is the third party, you are the first party, and the entity you want to talk to being the second party that is being verified by the certificate authority. Now, the certificate authority issues two main documents. One of them is called the Certificate Practices Statement, the CPS. This is the document that defines the practices, the standards, and the algorithms that the certificate authority will be using. This is usually a published specification sheet on their web server. You can go and retrieve and use this to compare their services to other certificate authority services. Also in this CPS document, they will define whether or not they use certificate templates. And again, templates are going to be pre-configured sets of elements to help automate and streamline the process of issuing certs to users and computers rather than having to fill out long, complex request documents. And very commonly, these are used in private networks, although they can be used somewhat on the public internet as well. But the second main thing that our certificate authority will issue is called a certificate policy. The certificate policy is effectively the rules that you as their customer have to follow. This will define what type of payment you must make. It'll define when payment is due. It will define the practices you can use certificate for. For example, they may dictate that you could or could not use it related to gambling content or violent materials, those kinds of things. They can also define that if you fail to inform them about any type of identity change, like say you change your domain name or you modify your business logo or some way that the certificate is verifying, then this would be a change of your identity, which is what the certificate is supposed to be checking on. And if you fail to notify the certificate authority made these changes and they find out on their own, this could be grounds for revocation. They'd also define other grounds of revocation, such as committing criminal activities, where the certificate was also a solid grounds for revocation. So a certificate authority is going to be the entity that verifies identity and stands behind that by issuing digital certificates. Let's look more in depth about the trust structures of certificate authorities. So the first certificate authority that is deployed is usually referred to as the root. Now, if you're working with a single authority environment, there is only one certificate authority, therefore it is the root, and all of the end users and devices all talk directly to that one entity. This is sometimes the deployment structure of smaller private networks. But in many cases, the root is only the first of many certificate authorities that are deployed. The root will self-sign its own certificates for itself to start a new trust structure, and then other certificate authorities deployed below it will have theirs signed by the root or the server above them. Now, any certificate authority that is located below another can be known as a subordinate or an intermediate. And there can be multiple levels or layers of certificate authorities in this structure. Now here, the certificate authorities can be single machines, where in this case, there are going to be, 7 different physical servers all working together in this deployment hierarchy. Or this could be a combination of multiple different entities, each of which being a certificate authority organization that then works with some dominant one. Now eventually we'll reach a level where the certificate authorities are going to be working with the end customers. And this bottom level or layer are often called leaf CAs. They're the ones who have direct customer interaction. Now, in some cases, one of these leaf CAs may be listed as a registration authority, as opposed to a leaf CA. The main distinction there is a registration authority is primarily focused on registering new customers, new clients with certificates, rather than doing any other work task. Sometimes this is an outside organization, an outside entity that is hired by the CA to offload the work of bringing in new entities. Often their job is to do some initial groundwork of accepting new applications and try to weed out any obviously fake or false or incomplete applications before the certificate authority itself spends the time and effort to do its full-fledged verification of background and identity. Now, this structure is known as a certificate hierarchy. This is a very common structure to be used by larger organizations as well as by public certificate authorities. Now, the root CA, once it has been used to deploy the next subordinate layer, is often turned off and left offline, usually in a secure vault, so that its keys are not logically accessible. That's because this entire trust structure is dependent upon the root itself. And so if anything ever happens to the root, then the entire system will fall apart. And so what usually happens is the root is kept offline, and then just before the certificates of the first level of subordinates expires, the root CA comes back online, issues new subordinate certificates to the next level, and then goes back offline moments afterward. In this way, it keeps it safe from any type of logical attacks that may occur throughout the remaining time frame, typically a year, that the subordinates are active. And for the most part, only the leaf CAs talk with end customers. The rest are kept isolated in doing other types of management tasks or establishing this trust structure rather than dealing with end user systems. So this is the example or the idea of both standalone and then hierarchical structures for trust between root and subordinate certificate authorities. So let's compare internal versus external certificate authorities. An internal CA is deployed for use inside the private organization, while an external CA is used for the public in general. So an internal CA is going to be installed, configured, and managed by the organization themselves for their own internal use. And this can be deemed as a cost savings because they don't have to spend money on getting certs from an outside public certificate authority. Therefore, they're free to build the certificates. They can freely distribute the trust as needed to all the members of their private organization. And if they so choose, they can even issue certs to entities outside their organization if that happens to be more convenient. Although they would then have to expose their CA server to outsiders so they can actually perform things like revocation checking, that kind of thing. So they'd have to potentially publish their certificate authority in a DMZ for public access if they choose to do that. Now, generally, an internal CA is not trusted by the overall outside world because it's an internal CA. It's not gone through the typical process of becoming well known and vetted by existing CAs or trusted by the world at large. And so generally, the general public is not only not aware of the internal certificate authorities, they therefore don't trust them either. Whereas if you are a contractor with a company that have a private CA, you could decide to trust them because you know the company and you want to be able to do work with them, and therefore you trust the CA because they exposed it to you, not because anyone in the outside world was informing you that they were a trustworthy entity in the first place. And this does, however, end up causing more administrative overhead for the hosting organization because they now have to install it and manage it and oversee it from that point forward instead of handing it off to a third party. Therefore, it's a bit more admin intensive to run your own internal certificate authority. An external certificate authority, however, is run by some public entity. You probably know many of these, VeriSign being probably the most common and most well-known, DigiCert being another example. So these are configured by third parties, but in most cases you must pay to use their certificates. Therefore, this is not as inexpensive a solution for you as a business entity. For the most part, public external certificate authorities are going to be paid certificates issued to companies or businesses or web servers for the public to use. Generally, most end users don't end up getting a certificate, although there's a growing movement now to allow end users to get individual certificates to prove who they are as well. They do cost money. There is no direct access granted to the certificate authority itself, meaning that the root of the certificate structure is often offline or hidden, and only some leaf CAs at the bottom of their hierarchy are exposed to the outside world. And for entities that are using certificates in this way, like businesses, it's less overhead for them, less management, because they simply have to abide by the rules and terms of the certificate policy from the certificate authority, pay the fee to get the certificate issued, and to sell it onto their system. There's no other management for them, because that's all done by the public external certificate authority. Now, the benefit to this is that now the entire public has the chance to be aware of the certificate authority and potentially trust in it. And if you happen to work with one of the already large dominant players in the certificate authority field, like VeriSign and DigiCert, you already have an installed market base where almost every browser and most other applications already trust in those certificate authorities. Therefore, it's going to quickly allow the world to trust in your resource as well. So this is the comparison between internal and external certificate authorities. So we've looked at the basic ideas of internal versus external structures of CA deployment, but there's several other terms that often come up. We wanted to look at those as well. So another term that often falls under the internal moniker is that of standalone. Now, standalone can end up referring to a deployment of two different options. It can either be referring to an individual certificate authority deployed just one of them, and then it handles the entire organizational structure for a private organization, or it is one that is not integrated into the organization's directory service. And in a true standalone, meaning it's not integrated or non-integrated, it does require the manual process to have certificates issued. While an integrated standalone is often known by the term enterprise, because it's likely one which is integrated into the directory structure, the directory service, and therefore issuance can be more automated. Now, in many cases, you may also end up having hierarchical as an internal system, and this is usually done when a single machine on its own isn't sufficient to handle the resource needs of your entire private organization. It is much more common for external machines to only be hierarchical. External CAs should only be hierarchical because you're trying to support the entire internet, and therefore there's a huge customer base, and you need the distribution and the workload power that a hierarchical structure would provide you. You also have the idea of commercial is much more common to exist on the internet. Where you're going to be having someone pay for the operation to use the services of an external CA. That's not always the case, but it is possible that you have to pay for them while they're external, while most of the time an internal CA is one that your use of them is provided for you because of your presence as an employee of the organization. Externals are more often than not public, hence the idea of external, versus internals are generally private. Although there are now sometimes use of internal CAs for public use, such as when a company decides to issue certificates to outside contractors and suppliers. That's when they're now treating their internal private CA as a kind of a public CA at the same time. The Department of Defense, for example, does this very thing, where many times private sector businesses are issued certificates so they can interact with them on a secure basis and provide strong authentication, but they're using a private CA for public purposes. And then you've got free versus paid. Again, most of the time, internal certificate authorities are for free use of employees, and generally public CAs or external CAs are more likely paid than not. Although there's a growing number of free options. There's a new service out now that's called Let's Encrypt, which does offer free certificates to web services in order to provide them with the ability to get up and running quickly with no out-of-pocket expense to provide encrypted and authenticated TLS web services. There's not yet an equivalent free option for regular individual users, but maybe one will come out in the future. So as you can see, there's lots of different terms that may come up when you discuss the certificate authority structure and hierarchy. So enabling trust is a core part of taking full advantage of a PKI implementation, whether in a private environment or on the public internet. Is the same idea. Establishing trust is ultimately an exchange of public keys. Now, you might first think, wait a minute, aren't public keys for anyone to use? They're for the public use, and aren't those exchanged in plain text? Absolutely they are. But the issue is when you purposely choose to retrieve someone's public key and then use it, and then someone else takes your public key and uses it as well. You're both agreeing to participate in the communication with each other. Now, the public key itself isn't what's going to support the exchange of anything secretive, but it starts off the conversation for us. As we saw earlier, it's the foundation of the idea called the digital envelope. When I grab someone else's public key, I can encrypt something with that public key, crafting it into what is called a digital envelope, and now no one else can open it but that particular recipient. And so this is the starting point of a trust relationship. With certificates, your systems have a local list of public keys of certificate authorities that you trust, and that's known as the Trusted Roots list. You can also add additional certificates to this list when you decide to trust individual entities outside of that. So you can try to trust individual people or businesses or individual machines by adding their public key to your own local trust list. Once you have added someone else's public key to your trust list, you now have trust in them. And if they've done the same to you, putting your public key in their list, they now trust you. So this means either side can now initiate a secure conversation. So enabling trust is a core element of establishing secure communications, secure exchange, and it's all underneath the umbrella of PKI. Certificates are used as a tool for authentication. They help establish trust, and they help us establish communication pathways that can be used for encryption and other forms of verification processes. So a certificate ultimately is a way to identify a subject identity. They're issued by a certificate authority, and from that we can then infer someone's identity through this third-party mechanism. Now, certificates can be issued either in a self-issued context or in a third-party context. Now, self-issued comes up in two different situations. One of those is when you have a single standalone device or certificate authority, and it might issue certificates to itself. This is somewhat common in private environments, as well as if you use services like, say, PGP, Pretty Good Privacy, an email encryptor. You're going to be your own self-signing certificate authority for your system. But a second condition where self-signing occurs is on the root certificate authority server. In this trust structure known as hierarchical trust, the top machine, the root of the certificate server grouping, is self-signing. It must sign its own certificates for itself. Then every subsequent level will then have a certificate signed by something above it, and that's known generally as either subordinate or hierarchical issued trust. Now, certificates are based upon public keys, and when combined with their corresponding private key, they are a solid basis for the concepts of digital signatures and digital envelopes we covered in a previous module. So, with the use of certificates, we can establish trust and maintain those relationships on a secure basis. Certificates are used through a variety of computing technologies. They're used for storage security, they're used for communication security, and several management activities. This includes things such as EFS, the encryption file system, which is the file-by-file encryptor found on the NTFS file format within a Windows operating system. It uses the public keys and private keys provided by a digital certificate to perform file-by-file encryption. Then there's SMIME, Secure Multipurpose Internet Mail Extensions. This is the standard for gaining digital signature and digital enveloping with encryption services within typical standard email communications. There are also third-party proprietary solutions like PGP, Pretty Good Privacy, you can use as well, and both are based upon certificates. Although SMIME is founded upon standard certificates, the X.509 version 3, while PGP uses proprietary or custom certificates just for PGP. Web servers use certificates to help identify who they are and initiates the negotiation of the TLS session to give you secure communications. IPsec uses certificates for authentication. It's one of the many things it supports. In addition to passwords and Windows authentication, there's certificate authentication supported by IPsec, and definitely the certificate authentication method is preferred over the other two options. We've got entity authentication. Anytime you want to verify or prove who someone is, certificates are the method by which this can be accomplished effectively. As you now know, certificates are a form of trusted third-party authentication. And as long as both the first and second parties both agree to abide by the terms and believe in and trust in the third-party certificate authority, then therefore they can trust each other's identity that's being verified or vouched for by the CA. The data recovery agent, this is a special admin task or admin function that if a particular user or worker happens to have their certificates corrupted or lost in some way, or maybe they've lost their credentials to log in to use their certificates, then a data recovery agent can go into their system and recover their data for them. This is a common component in the EFS encryption file system, where if for some reason your user's credentials are corrupted or lost, you would lose access to all of your encrypted files. But if your system has a data recovery agent defined, they can come into the machine on your behalf with their admin credentials, unlock an additional container of the symmetric keys of each file, unlock the files, and give you back the plain text file. So they're recovering the data itself. Now, another related type of agent is the key recovery agent. These are the agents that can go into a backup or an archive of certificates and keys and recover those exact keys and hand them back to the user. Let's say that you happen to have an environment where you are storing your certificates on a smart card. And for some reason, your smart card got dropped into the paper shredder and got destroyed. Since we know this wasn't a theft or falling into the hands of an enemy or a bad guy, there's no risk of reissuing you those certificates again. And so the key recovery agent would go into the backup of the organization's certificate store, retrieve your certificates, put them on a new smart card, and hand that back to you. We also have services like Kerberos, which is the foundation component of Microsoft's Active Directory, and it now supports the use of certificates for authentication. We have enrollment agents. These are the entities that a certificate authority or other entities may use to help support new enrollments, whether that be to get new certificates or enroll into an organization or enroll into a website or add yourself as a user in some way. Many of these services will use certificates to initiate their identity and verify who they are to you, as well as issuing certs to you as part of that process. And then also code signing. Code signing is a way for us to use certificates to help verify the origin or source of code. This is an important component of interaction on the internet where you don't always know where software code comes from. And since we use a variety of software code, what we might call mobile code, on web services, it's important to have that code signed so when it reaches your machine, you can at least have some knowledge of who the origin was and therefore make the decision with some informed consent on whether it's worth the risk of running the code or not. So when you reach out to a certificate authority to get a certificate issued to you, you need to understand some basics about how that issuance might happen. So there are two main ways it can occur. There's more of an automated process and there's more of a manual process where some administrator of the certificate authority has to verify or approve and walk through the steps of actually issuing the certificate. So let's first talk about the idea of auto-enrollment. So auto-enrollment would occur often in a private environment, although there's a number of public situations where you may be able to auto-enroll as well. One of those is called Let's Encrypt, where you're able to get your web server or your website enrolled automatically with a basic certificate that lasts for 3 months at a time. But the idea of auto-enrollment is you get a certificate by simply applying based upon a pre-built certificate template, and either you pay if it's necessary to do that, or for free, the certificate's issued to you automatically, but there are often very limiting conditions where the auto function would actually take place. So that's auto-enrollment, where it's issued to you simply by you making the request for and filling in all the right details of the request site, which is more likely than not a web interface. Then you also have the manual enrollment, which is what most CAs have. And you can either have this enrollment take place out in the public internet or in your private environment as well. Out in the public internet, you'd visit a website of a certificate authority like DigiCert or VeriSign, and you would go through their web interface to make a formal request. You provide your details of your identity, you provide payment information, and then the certificate authority would then spend the time and effort to perform a verification of your identity. Now, once they're satisfied with that, then they'd issue the cert to you. And they'll do this in a manual process. Now, in the back end, how this manual process might work is they may likely have a native or default console based upon the certificate service application they're actually using. Now, if you happen to be working with a Microsoft Windows supported environment, you're likely using the MMC, the Microsoft Management Console snap-in for certificates, and therefore you're using the Microsoft's interface, which would be, in fact, in the Windows world, a native console there. And so an admin would have to go through the steps of checking on the request, making sure all the details that were needed for an application are present, and then start the process of verification. And once satisfied, the verification process is complete. They'll then click through the remaining steps in order to formally create the certificate by signing it with their private key and then distributing it or issuing it back to the requesting subject. Certificate management is about dealing with certificates throughout the life of their use. Now, one of the key things to keep in mind about certificates is that they're issued for a particular period of time. Therefore, they have an expiration date. And so one possible status of a certificate is expired. An expired certificate is no longer valid. Its serial number is no longer to be used by that certificate authority. And once this has happened, this should be now one that's discarded. And if you need to have a new one, you have to go through a process that's called reissue. Now, reissue can be a problematic term in English because it kind of seems to imply that I'm going to be issued back the one I had before. But that's not really what happens here. Instead, this is a shortened form of the phrase repeats the issuance process, where you'll go back and completely re-perform the entire procedure of obtaining a certificate. And so ultimately, you're going to be getting a new serial number. And therefore, it is a new certificate, and the pre-existing trust relationships you had with your previous certificates are no longer relevant. Those are tied to the now expired certificate. Now you have to go and reestablish all of those trust relationships. Now, if your certificate authority offers this, you can go through another option called renew or renewal. Renewal, or to renew, is to extend the expiration date. If your CA allows this, you must complete renewal before expiration is reached, because once something is expired, it's no longer usable. So renewal takes place before expiration, but it keeps the same serial number. You simply have a longer length of time before expiration will be reached. So you extend the expiration date. Not every certificate authority supports or offers you renewal services. Now, in some cases, there may be a need to cancel a certificate. And that has a special name. It's called revocation. Now, we discuss elsewhere in our materials the ideas of revocation, which are known as the certificate revocation list and the online certificate status protocol method of querying to see if something has been revoked. But the reasons why something might be revoked is because potentially maybe your keys are compromised. And if so, then those should be discarded and replaced for new ones. It's also a possibility that you've ceased operations, and therefore because of that, you don't need the certificate hanging out there any longer, so you come in and get it revoked as well. Or maybe your certificate was used in a participation or functioning of a criminal activity. This is often grounds for revocation by the certificate policy. But more likely what would happen is that you've changed some aspect of your identity, which is being verified or proven by the certificate itself. And since that's the whole point of certificates, authentication, proof of identity, when your identity changes and you don't inform the CA and they find out about it on their own, that's absolutely grounds for revocation. So once something's been revoked, it's been canceled by the certificate authority and placed on the certificate revocation list. Now, sometimes there may be a need to temporarily suspend the use of a certificate, and that's called suspension. Suspension is effectively temporary revocation, where you're able to put your certificate on the revocation list in a special suspension subset or subsection, and while it's on the list in that way, it's treated as if it is revoked. But then when you come back for use, it can be taken off the revocation suspension list and go back to regular use. The only downside of suspension is that your expiration date doesn't change. So if you happen to put your certificate into suspension because your server is offline for repair for 2 months, you just give up that time frame of use while you're in suspension. So these are the basic concepts and ideas related to certificate expiration and certificate management that you want to be familiar with. Anytime your system receives something that has been signed by a certificate, you need to verify the certificate is acceptable, valid, and still okay for you to accept as proof of someone's identity. And as we've talked about, you go through the process of verifying that your system trusts in the issuing certificate authority and that the certificate has not yet expired. And then the last thing you check is whether or not it's been revoked. Now, what the process we use for this is based upon a concept known as the Certificate Revocation List, or the CRL. This is a document, a text file effectively, that is a listing of the serial numbers of the certificates that the certificate authority has canceled. Now, what you would like to do is retrieve this certificate revocation list each and every time you happen to receive a certificate assigned item, because you want the latest information in order to find out, is the currently used certificate still okay, or has it been revoked? The problem with this is certificate revocation lists grow in size over time. And so every time you retrieve the CRL for your use as an end system, you're causing some bandwidth cost on the part of the certificate authority. And just think of any public CA environment, they have potentially millions, if not hundreds of millions, of end users that are pulling and retrieving that CRL on a regular basis. And that's a lot of bandwidth cost. So in most cases, the certificate revocation list has a staleness date placed on it. This prevents you from downloading a new version until a certain period of time has passed since the last time you downloaded a version. Now, this may be only 2 or say 4 hours, or maybe as long as 48 or 72 hours. Now, the longer the length the staleness date might be, the longer you must go with a slightly out-of-date certificate revocation list, and thus there's a risk to you of accepting certificates that have been revoked, but which you are not aware of because you have a slightly out-of-date CRL. Now, this causes some security risks for you, the end user, but improves the cost for the certificate authority, but neither of these is beneficial ultimately in the long run. Now, there's some other issues with the CRL. If you are an outside entity and trying to access the CRL of an internal CA of a private environment, and again, you're on the outset of that organization, you might not be able to access and download the CRL because of where it's located. They would have to put on a public CA to offer the CRL to you, and that itself can be challenging for them to do. Now, they could potentially place this in their DMZ, making it a little bit easier to access, but then that's more of a complicated setup for the private environment. We also have to realize that you must download updates on a regular basis, and as an end user, you want those updates occurring every single time you need to verify certificate's revocation status. And again, that's contrary to what the certificate authority is going to want to do, because again, more frequent updates for you means more costs for them. And we also need to realize this is a lot of overhead and management. The certificate revocation list is always growing, it's always expanding, because once the CA has canceled a certificate or effectively revoked it, they never ever want to give anyone the opportunity to ever accept it again. Now, in the process of verifying a certificate is okay to accept, You do get the chance of adding in a new certificate authority that you don't yet trust, and you do get the chance to accepting a cert if it's expired. But what you don't get the chance to do is accepting a cert if it's been revoked, which means for this to be enforced, the certificate revocation list must maintain every single serial number that's ever been revoked of every certificate of that CA, and therefore it's always growing and expanding. So fortunately today, we have a replacement for the certificate revocation list, and it's called the OCSP, and that stands for Online Certificate Status Protocol. This is effectively a query-based system, not too much different from that of DNS, where you as the end user send a query to an OCSP server run by the CA, and then you get back a quick response saying, yes, this is valid, or no, this has been revoked. This means you get instant information for every certificate you want to check. Therefore, the client is satisfied. And from the server's perspective, the CA's perspective, they have a minimal amount of data to send back to you. Therefore, their overall bandwidth cost is much reduced, even though they're now communicating with you on every single time you check for revocation. So OCSP has been around now for well over a decade, and it's the dominant technology we use today to help check for revocation status. So whenever you're dealing with certificates, you also want to think about certificate storage. And there are two different contexts where we need to talk about this. First is the certificate authority itself. Now, again, as we've talked about, there are two main types of CAs. There are the internal ones and those that are external or public. So an internal CA is the certificate authority your company runs. And in most cases, when your organization is the certificate authority, when they create certificates for their workers and employees, they will keep a backup copy of both the certificate and the corresponding private key in an archive or a backup data set. Now, a public or an external CA usually does not ever get a copy of the private key in the first place. They only are ever given the public key from the subject who's making the formal request to get a certificate issued, and thus the public or external CA does have a backup or an archive of certificates, but it's only the public's portion of the certificate, not the corresponding private key. Now, a second situation where we have to concern ourselves with the storage or backing up of certificates is in end user, in subject, in devices. And there's a variety of things we can do here. So we could have it being stored on the system itself. And for things like web servers and database servers and email services is pretty common, where we have a storage on the system itself. Now, we want this to be secure, so this needs to be in either a protected file, an encrypted file, or a protected chip. In some cases, the TPM, the Trusted Platform Module chip on the motherboard, can be used as a certificate storage container because it is a tamper-proof concept of a computer chip. Now, for typical end users, we often want to store them either on the system itself, maybe as a file somewhere in the operating environment, maybe part of the user's profile, or we'll put it on removable media, where a smart card or a USB drive or some common methods we might use. Now, if we leave it on the system, so it's always present on the machine all the time, this is the most convenient for the user because they never have to think about it. It's already on their machine all the time. But that's also the negative of that. That means that in the event of a logical attack, then their certificate is already on the machine at all times to be potentially compromised. So a potentially more secure option is to use a removable media storage mechanism. Now, this is less convenient for the user because now they have to remember to take that item with them at all times. They must plug it into the machine when they want to use certificates and remember to unplug it when they want to leave the machine. If they use this technology properly, the certificate is only exposed to a logical theft from the machine while they're present and logged on. And whenever they log out and disconnect and leave the system, then their certificates are no longer on the machine. They're instead on this physical device they're carrying with them. Now, there also is a risk of loss or theft of that portable device, yes, but generally we think of that level of risk a little bit less than a logical risk on the machine at all times. Because if we have an internet-connected computer, whether directly or client retrieval level of internet connection, there's always a risk of malicious code or remote access attacks taking advantage of that digitally stored certificate locally. Whereas if it's on a mobile device, when it's disconnected from the machine, the risk is only someone that's physically proximate to you has the chance of picking it up or stealing it off of you. So the risk is less. So these are the ideas of storage certificates. We have the two options of used by a certificate authority. An internal CA, again, likely has both your public and private key components of certificates, while a public CA, external CA, typically only has the public side. And then from an end user perspective, we may store it on the system itself, store it in software, or maybe store it on a removable media device. One of the common means of storing certificates is on removable media, in this way that you only have the certificate itself on the system when your device is plugged in. One of the more common examples of the removable media form is that of a smart card, or sometimes known by its formal term, the Common Access Card, or CAC, as often used by various members of the DoD and military and other agencies of the government. Now, this is considered a smart card because of the chip that's present right here. This is known as a ISO 7816 chip, and it's that gold squarish-like interface that you may have seen on lots of cards and maybe even have on some of your credit cards now, that is able to be read by a device when it's put into a reader. We also have, in many cases, smart cards that have other features, but let's focus for a moment just on this ISO chip. For a digital certificate storage, it's this chip, the ISO chip, that is used to store information. It can have both processing abilities and memory capabilities built into it. So you can store multiple digital certificates on these cards, and when you plug them into a card reader, they can read the data off of them. And this way, your computer can be provided your certificates quite easily through this type of mobile device. Now, the benefit of using a smart card for this, as opposed to, say, a USB thumb drive, is that the card can be used for lots of other functions at the same time, such as this item here. This is an optical area where this information can be read with a camera as opposed to direct physical contact. We also have a clear presentation of the owner's name. We have a photo ID that you can see their face. We do have multiple places where the expiration date is located, and this way it's going to be challenging and difficult for someone to easily falsify or change the expiration date on the original card. And there may be other parts as well. The back may have a magnetic stripe that's readable a lot like our older credit card style options. There may be other types of optical information present on the back. And there may even be internally a concept known as RFID, radio frequency identifier, which is a way to be able to send radio signals by having a special antenna inside the card itself, that when that's in a certain magnetic field, it produces an electrical current in the antenna, and this antenna powers the chip, which then transmits an electrical signal, a radio wave signal, to a nearby recipient, nearby device, to pick up that code. This might be used to, say, unlock doors or access certain equipment, that kind of thing. So this is an example of a smart card which has the ability to not only store certificates via the ISO 7816 chip, but has many other functions as well. We've discussed in this module the idea of certificates and how they're issued and how they operate, but what we haven't really covered in depth is the idea of certificate management. And if you're choosing or electing to install certificates and run them yourself in your own organization, there's a lot of things to think about. Let's take a look at a few of the questions you're going to have to answer before you begin rolling out your own certificate infrastructure inside your own private organization. First off, how many certificate servers are you going to need? If you have a small organization, one certificate authority server may be sufficient, but as you grow into the thousands or tens of thousands or larger in terms of the number of devices or users that need certificates, a single server may become overburdened, and therefore you may have to actually go from a single authority trust to a hierarchical of trust, where you have to have an initial root and then have one or two levels, or if not more levels, of expanding connections of multiple certificate servers. You want to make sure that the bottom level, your leaf CAs at the bottom level of your hierarchy, are numerous enough to handle the workload of the amount of systems that are both being requesting, managing, verifying certificates throughout their operational use. And therefore, this can be a challenge to figure out in the very beginnings of your deployment. Next, how are you dividing up your certificate types? And do you even have different types? Now, out on public certificate authorities, there are a variety of types that are worth considering. First is the idea of an extended validation certificate. These are certificates that are issued because the certificate authority has spent a bit more time and effort to verify and focus in on the identity of the subject entity. They go more in depth. They do require a few more elements to be true, such as the subject must have already had a certificate for a period of time, have paid their bills properly, not had any significant complaints, or any complaints were resolved correctly, those kinds of things. And the certificate authority will go through a bit more extra verification process and then issue an extra extended validation certificate. Now, you might recognize these in your browser as you visit certain websites, and you can tell the difference between a regular issued certificate and an EV certificate because the padlock in many browsers will now turn likely green, and then beside the padlock, the name of the verified organization will now appear there. Whereas if you go to a non-EV certificate site, you'll only see the padlock on its own, usually in whatever default color it might be. So try this experiment on your own. Go visit first google.com, which will always be a signed encrypted location. And you'll notice there's a regular lock padlock in most browsers. But then go visit the website of Symantec.com, and you'll see that because Symantec now owns VeriSign, they have issued themselves an EV certificate, and you'll see the Symantec Incorporated corporation name listed right beside the now likely green padlock. But there are many other types of certificates you might also want to consider deploying or issuing or simply being aware of. There are the organizational certificates. Those are ones that are going to be identifying the whole entire organization. There are domain certificates, which only identify systems that are falling underneath the main registered domain name of an organization. There are also individual device certificates for identifying one particular machine, and you've also got individual certificates identifying one individual person. And another nuance of certificate types is the length of their validity. Now, in general, 1 year is pretty common, but you can also have certificates issued for 3, 5, 7, even 10 years, or you can go shorter. 6 months or even 3 months are also now available in certain situations. So what types of certificates do you want to issue, and what length of time do you wish to have them valid for? Another concern is, do you need subordinate CAs? And as we talked about in the first question, if a single certificate authority isn't going to be robust enough to handle all of your certificate workload, you definitely will need subordinate CAs in a hierarchy structure. Who's going to administer the certificate authorities? Is that simply another task you're going to put on top of your existing IT department? Is that going to go on the shoulders of the security administrator? Or do you need a separate certificate authority admin, a new job position? And in some cases, one person may not be enough. It may take 3, 4, or 5 people to actually manage that properly for an enterprise-sized global organization. Are you going to be using certificate templates? This may be a useful technique if you want to help make the issuance of certificates to users or devices that are similar in nature. You can have pre-crafted certificate templates that minimizes the effort needed by either you, the admin, or the in-device manager or the subject to have to fill in extra things by having most of the information that is standardized or common pre-populated in those templates. What is your policy for backups? And are you going to retain a backup of both the certificate itself, which again is based on the public key, but also the corresponding private key? Now, if you do retain both the public key and the private key, you're likely dealing with an internal private CA situation, and you would only do this if you actually want the ability to perform 2 possible tasks. Either perform the key recovery agent concept, where you want to be able to restore keys back to end users if they're ever lost or corrupted, but you also may want to have the ability to provide those keys in the event of a legal investigation. If there's a criminal activity and forensics requires the private key of a potential suspect or even just a regular user who may have been a victim to unlock data that may be evidence, they may want to have a copy of those private keys. And therefore, having those keys in your own backup gives you the ability to create an escrow of your backup of your key database and provide that to the law enforcement group doing the investigation. Now, I said the word escrow here. Now, you may have heard that term related to a mortgage, where you pay money to your mortgage bank, and they hold it for you so that once a year they can pay your insurance and your taxes. And basically what escrow means is in the hands of a third party. And in light of a certificate database, if I have a backup copy and I give that to a third party, then that third party now has an escrow of my backup database. And then one more question is, what is my procedure for certificate approval? I should formally define how we're going to check out and verify that a requesting entity is valid. Now, for some things like devices and regular workers, this might almost always be a nearly automated or fully automated procedure. But as we begin to offer more esoteric or unique or one-off certificates, we may actually require a human to go through a process of step-by-step verifying the identity of the entity, checking with procedures and filling in details, and then formally issuing the file and transferring it to the end device or end user in a secured, controlled distribution method. So we need to define those processes. Whether we are using automated or doing mostly and only manual, again, define the standard operating procedures for that. So these are just some of the things you're going to have to figure out if you're going to be implementing your own certificate system inside your organization.